All right, so everybody who's just joined us online, welcome. Let me just show some simulations. So here's the full preemption and rent dissipation simulation, which confirms the Reardon and Salant result. You can see that this black line here, this is deterministically decreasing state-of-the-art technology with small steps because the dt is really small. So we're trying to think of the kind of being close to continuous time. On the vertical axis, so the horizontal is time. The vertical axis is the marginal costs for all different C's, right? And the blue line here is the monopoly solution. These are investments at optimal times by a monopolist in order to maximize profits. The problem is when to invest, right? So like for how long you wait before you invest such that you maximize overall discounted profit. And in the oligopoly case, you see that one firm never invests. This is a green line. And then the other oligopolist invests a lot more frequent than the monopolist. And this leads to this rent dissipation. Basically, the net present value of their profits is becoming zero just because they invest too often. But you can look at other simulation. We look at other simulations. We are able to have the underinvestment case where the monopolist would invest more frequently than one of those oligopolists. You can see that the green line corresponds to the investments which are less frequent. For what the k is relative low relative to dt, and then we have all sorts of leapfrogging. So when k is even lower, this is the leapfrogging simulation, right? The green and red line are kind of going in time and represent the equilibrium that we had in mind all from the start. And then you have leapfrogging with random alternation. It's not possible to say from the graph, but there is some stochasticity in who has the right to move. Over here, you have instances when the technology does not improve. You have this slightly longer steps, that enough to induce leapfrogging, or when you have large changes in the state-of-the-art technology that also kind of gives you leapfrogging in a typical simulation. Now, let's talk about symmetry. So this is the assumption which simplifies the solution of many games in dynamic games, right? And it's quite useful in a lot of the settings. So if I said that my competitors would be completely symmetric, so the value function of firm 1 would be exactly like the value function of firm 2 when I switch their costs. Because we solve for everything, we can just basically check what are the equilibria where this condition holds for every point of the state space. So if we restrict ourselves to only these symmetric solutions, well, they're highlighted here. These large points on the diagonal, these are the only equilibria that satisfy symmetry over the whole state space. Now, maybe that's not that important because the equilibrium path may not cover the whole state space. But as soon as you have that additional taste shock in your payoffs, as long as this taste shock has full support, then there is a small probability of making an investment at each point of the state space. And that kind of immediately includes the whole state space into the equilibrium path. And so this is not an innocuous assumption, at least in this setting. We don't want to, we can't say anything more general or more, but just in this numerical simulation, turns out that the interesting efficient equilibria close to the diagonal line are just washed out by imposing symmetry. Now, what about homotopy? I think this idea came about during the week a couple of times. And I showed that graph with the homotopy, which really looked very nice. Where was it? Here. So remember, these are the best responses for the players which don't have taste shocks. And if you do, then the best responses become these nonlinear functions, which are kind of hard to deal with. And as you change the scale of the taste shock, then there is this nice convergence of the best responses from this kind of more complicated curvy lines to the step functions that are much easier to deal with. And so that would be a really natural homotopy to explore in this problem. Moreover, if taste shock is large, that's kind of moving the behavior of the firms to flipping a coin, right? You're just taking a choice randomly. And then, of course, there's uniqueness, right? Everybody's just randomly making the investment choice. There's not going to be scope for any multiplicity. And so that's the idea of homotopy method. You can solve the model in a simple to solve region, and then move the parameter to move the whole solution into the region where it's much harder to solve by following the path of the solutions as this parameter changes. For us, the very natural homotopy parameter would be the scale of the taste shocks. Well, the problems with the multiplicity of equilibria is that there are too many bifurcations. You know, as this parameter changes a little bit, then suddenly you have an explosion of equilibria. And so following that path is going to be pretty hard. This is an illustration. This is the scale parameter for the taste shock, and this is just a value function in the apex of the game for one of the firms. And you can see that, you know, you could follow this path, and this probably is a loop which is not important first, but then, you know, it's very, very quickly gets into this large multiplicity that makes the path following harder. In fact, you know, this payoff maps change when you change the parameter, and we thought that the best way to actually show them to you would be to play a movie. So look at this. This is the payoff map that you've seen, and there's a single equilibrium. I'm moving eta, the scale of the shock, and you know, as this moves slowly, suddenly you have these dots just kind of exploding, just appearing out of nowhere on the payoff map. Some are moving somewhat continuously, but in general, there are this completely new solutions that appear and disappear. And you know, eta is not the only parameter which has this this behavior. Let's see, is this all for this movie? Here's another. It's not very often that you get to show movies. You would understand by remembering the name of this composition.
Oh, that's from Rust Never Sleeps by Neil Young.
Yeah, exactly.
He's working all the time.
So moving any parameter essentially leads to this the equilibria, well, at least in this representation, kind of appearing and disappearing. And yeah, there is some continuity in how these dots move around. This is the transition probability for the right to move. The fact that these equilibria kind of appear out of nowhere as you change the parameter, this is kind of foreshadowing a little bit to the how would the MPAC estimator work in this case. Essentially, right, the MPAC estimator imposes equilibrium restrictions of the model. But if, as you change the parameter, these restrictions discontinuously kind of move around in the parameter in some space, that makes it really hard to perform constraint optimization. So that's one of the reasons why MPAC estimator may fail in this setting. But let's come back to that.